Dear students, welcome to this course of Model-Driven Software Engineering. My name is Timur Umarov. In this course, you will learn a new approach to software engineering called Model-Driven Architecture, MDA. Model-Driven Software Engineering represents a new different philosophical approach to the software development field. Older ways of creating requirements for the software and designing computer programs have proven to be not effective and efficient enough in many ways, including productivity, portability, documentation, and so on. MDA is an alternative vision on the traditional software development cycle, which entails viewing systems as models. This abstracted view on systems that are being designed allows developers to perform high-level reasoning about these systems in order to concentrate on and emphasize software's conceptual properties and general aspects without being preoccupied too much with its details. This makes the MDA framework an approach which potentially deserves attention from the modern computer science community due to its multiple advantages as opposed to the traditional software engineering. This course is particularly designed for postgraduate students majoring in computer science, software engineering, and other related subjects. The syllabus for this course you can find on DL. My email address is shown on this slide. We are going to start this lecture with traditional software activities and bring up some definitions for the purpose of revisiting what you have learned during your undergraduate stints. Otherwise, if you are new to software engineering, it can be a little challenging for you, but stay tuned because the slides in what follows are quite thorough and provides as much explanation as possible. So let's ask ourselves a question. What is a software? The most obvious answer to this question is that software is a computer program or a set of computer programs and associated documentations. Software products may be developed for a particular customer or may be developed for a general market. If we want to separate professional software from amateur one, we should emphasize that professional software is a complete software package that usually includes one or several separate programs, configuration files, system documentations, user manuals, and the website for program updates. Software engineers are primarily interested in developing software products, and by that we mean software which can be sold to a customer. To this effect, there are two kinds of software products, generic and customized. Generic products are standalone systems that are produced by a development organization and sold on the open market to any customer who is able to buy them. Examples of this type of product include software for personal computers, such as databases, word processors, drawing packages, and project management tools. Examples are Microsoft Word, Microsoft Access, Adobe Photoshop, and so on. It also includes so-called vertical applications designed for some specific purpose, such as library management system, accounting systems, or systems for maintaining medical records in a hospital. Customized or bespoke products are systems that are commissioned by a particular customer. A software engineer develops the product especially for the customer. Examples of this type of software include control systems for electronic devices, systems written to support a particular business process, and air traffic control systems. Based on the formal definition borrowed from widely known literature on software engineering, a software process is a set of related activities that leads to the production of a software product. These activities may involve the development of a software from scratch in a standard programming language like Java or C. However, business applications are not necessarily developed in this way. New business software is now often developed by extending and modifying existing systems or by configuring and integrating so-called off-the-shelf software or system components. We all believe that the process of producing software is a creative process, so automation of such processes is quite limited. However, there are attempts to automate several steps that are considered common to any processes, and such attempts are implemented in so-called computer-aided software engineering tools. But again, there are many different software processes that are related to the large variety of target domains, but all must include 4 activities that are fundamental to software engineering. Software specification includes the functionality of the software, and constraints on its operation must be defined. Software design and implementation means that the software produced must meet the specification. Software validation requires that the software be validated to ensure that it does what the customer wants. Software evolution specifies that the software must evolve to meet changing customer needs. In some form, these activities are part of all software processes. In practice, of course, they are complex activities in themselves and include sub-activities such as requirements validation, architectural design, unit testing, and so on. There are also supporting process activities such as documentation and software configuration management. When we describe and discuss processes, we usually talk about the activities in these processes, such as specifying a data model, designing a user interface, and the ordering of these activities. Producing software is never easy. Too many details to take into account. However, abstracting from the details simplifies the whole process. Engineers reason about general aspects and structure the models rather than working on their details. This in turn enables them to effectively deal with complexity and allows to represent and view the software product and process as an abstract entity to simplify understanding and implementation tasks. The deliverable from every stage of software development is a respective model: requirements model, specification model, architectural model, detailed design model, and program model. The waterfall approach takes the above activities and represents them as separate and distinct process phases, such as requirements, specification, software design, implementation, testing, and so on. After each stage is defined, it is signed off and development goes on to the following stage. Iterative development approach interleaves the activities of specification, development, and validation. An initial system is rapidly developed from very abstract specifications. This is then refined with customer input to produce a system that satisfies the customer's needs. The system may then be delivered. Alternatively, it may be re-implemented using a more structured approach to produce a more robust and maintainable system. The first published model of the software development process was derived from more general system engineering processes back in 1970. Because of the cascade from one phase to another, this model is known as the waterfall model or software lifecycle. The principal stages of the model map onto fundamental development activities: requirements analysis and definition. The system's services, constraints, and goals are established in collaboration with system users. They are then defined in detail and serve as a system specification. System and software design. The systems design process partitions the requirements to either hardware or software systems. It establishes an overall system architecture. Software design involves identifying and describing the fundamental software system abstractions and their relationships. Implementation and unit testing. During this stage, the software design is implemented as a set of programs or program units. Unit testing consists in verifying that each unit meets its specification. Integration and system testing. The individual program units or programs are integrated and tested as a complete system to ensure that the software requirements have been met. After testing, the software system is delivered to the customer. Operation and maintenance. Normally, although not necessarily, This is the longest life cycle phase. The system is installed and put into practical use. Maintenance involves correcting errors which were not discovered in earlier stages of the life cycle, improving the implementation of system units and enhancing the system's services as new requirements might well be discovered. In principle, the result of each phase is one or more documents that are approved. The following phase should not start until the previous phase has finished. In practice, these stages overlap and feed information to each other. During design, problems with requirements are identified. During coding, design problems are found and so on. The software process is not a simple linear model, but involves a sequence of iterations of the development activities. If overlapping frequently occurs between stages, prototypes are developed for examination by system users and developers to have an understanding that the whole development process is going in the right direction, until it is too late. The obvious advantages of having prototypes can be summarized by having so-called quick and dirty example solutions for examination by system users and developers. These prototypes by structure and are reminiscent of implementation programs, so it is easy to transform these prototypes into final implementations. Let's now look at the advantages and disadvantages a waterfall lifecycle has to offer. Among the advantages, of course, it is a disciplined approach to software development, facilitates more effective project management with clearly defined milestones. Opposite to this advantage, we can observe several disadvantages. Firstly, it is hard to follow precise deadlines for requirements completion, which can endanger the whole project. Secondly, so-called monolithic approach that is practiced in the waterfall lifecycle may lead to long time until the final product is delivered. Thirdly, it is not easy to handle system complexity, as the well-known classical method, divide and conquer, is not provided for. And of course, no scope for abstraction. Another advantage is that a complete documentation is produced at the end of the software development project, which is a strong side of this method. However, no one can guarantee that this documentation is a useful and even valuable material because of lack of preciseness and the risk of bureaucratizing the whole process. Another advantage is that it is easy to legally clarify the position of the development team in terms of where they are in the project due to rigid signing off procedure embedded in the waterfall lifecycle. However, we all know that the software development process is a social process, and we must admit the fact that requirements constantly change, which brings on another level of difficulty. And last but not least, at the initial stages, it requires careful project planning. However, at the initial stages, the estimated resources needed for the project are not precise and often inadequate. Change is inevitable. In all large software projects, the system requirements change as the business procuring the system responds to external pressures. Management priorities also change. As new technologies become available, designs and implementation change. This means that the software process is not a one-off process. Rather, the process activities are regularly repeated as the system is reworked in response to change requests. Iterative development is quite fundamental to software. Here, we introduce the topic by describing two process models that have been explicitly designed to support process iteration. First is incremental delivery. The software specification, design, and implementation are broken down into a series of increments that are each developed in turn. Second is spiral development. The development of the system spirals outwards from an initial outline through the final developed system. The essence of iterative processes is that the specification is developed in conjunction with the software. However, this conflicts with the procurement model of many organizations where the complete system specification is part of the system development contract. In the incremental approach, there is no complete system specification until the final increment is specified. This requires a new form of contract, which large customers such as government agencies may find difficult to accommodate. The waterfall model of development requires customers for a system to commit to a set of requirements before design begins, and the designer to commit to particular design strategies before implementation. Changes to the requirements require rework of the requirements, design and implementation. However, the separation of design and implementation should lead to well-documented systems that are amenable to change. By contrast, an evolutionary approach to development allows requirements and design decisions to be delayed, but also leads to software that may be poorly structured and difficult to understand and maintain. Incremental delivery is an in-between approach that combines the advantages of these models. In an incremental development process, customers identify in outline the services to be provided by the system. They identify which of the services are most important and which are least important to them. A number of delivery increments are then defined, with each increment providing a subset of the system functionality. The allocation of services to increments depends on the service priority, with the highest priority services delivered first. Once the system increments have been identified, the requirements for the services to be delivered in the first increment are defined in detail, and that increment is developed. During development, further requirements analysis for later increments can take place, but requirement changes for the current increment are not accepted. Once an increment is completed and delivered, customers can put it into service. This means that they take early delivery of part of the system functionality. They can experiment with the system that helps them clarify their requirements for later increments and for later versions of the current increment. As new increments are completed, they are integrated with existing increments so that the system functionality improves with each delivered increment. The common services may be implemented early in the process or may be implemented incrementally as functionality is required by an increment. This incremental development process has a number of advantages. Firstly, customers do not have to wait until the entire system is delivered before they can gain value from it. The first increment satisfies their most critical requirements, so they can use the software immediately. Secondly, customers can use the early increments as prototypes and gain experience that informs their requirements for later system increments. Thirdly, there is a lower risk of overall project failure. Although problems may be encountered in some increments, it is likely that some will be successfully delivered to the customer. Fourthly, as the highest priority services are delivered first and later increments are integrated with them, it is inevitable that the most important system services receive the most testing. This means that customers are less likely to encounter software failures in most important parts of the system. The spiral model of the software process was originally proposed by Boehm in 1988. Rather than represent the software process as a sequence of activities with some backtracking from one activity to another, the process is represented as a spiral. Each loop in the spiral represents a phase of the software process. Thus, the innermost loop might be concerned with system feasibility, the next loop with the requirements definition, and the next loop with the system design, and so on. Each loop in the spiral is split into 4 sectors: objective setting, risk assessment and reduction, development and validation, and planning. In the objective setting, specific objectives for that phase of the project are defined. Constraints on the process and the product are identified, and a detailed management plan is drawn up. Project risks are identified. Alternative strategies depending on these risks may be planned. In the risk assessment and reduction sector, for each of the identified project risks, A detailed analysis is carried out. Steps are taken to reduce the risk. For example, if there is a risk that the requirements are inappropriate, a prototype system may be developed. During the development and validation sector and after risk evaluation, a development model for the system is chosen. For example, if user interface risks are dominant, an appropriate development model might be evolutionary prototyping. If safety risks are the main considerations, development based on formal transformations may be the most appropriate, and so on. The waterfall model may be most appropriate development model if the main identified risk is subsystem integration. In the planning sector, the project is reviewed and the decision is made whether to continue with the further loop of the spiral. If it is decided to continue, plans are drawn up for the next phase of the project. The main difference between the spiral model and other software process models is the explicit recognition of risk in the spiral model. Informally, risk simply means something that can go wrong. For example, if the intention is to use a new programming language, a risk can be that the available compilers are unreliable or do not produce sufficiently efficient object code. Risks result in project problems such as schedule and cost overrun, so risk minimization is a very important project management activity. A cycle of the spiral begins by elaborating objectives such as performance and functionality. Alternative ways of achieving these objectives and the constraints imposed on each of them are then enumerated. Each alternative is assessed against each objective, and sources of project risks are identified. The next step is to resolve these risks by information gathering activities such as more detailed analysis, prototyping, and simulation. Once risks have been assessed, some development is carried out, followed by a planning activity for the next phase of the process. The Rational Unified Process, or RUP, is an example of a modern process model that has been derived from work on the UML. The RUP recognizes that conventional process models present a single view of the process. In contrast, the RUP is normally described from three perspectives. First, a dynamic perspective that shows the phases of the model over time. Second, a static perspective that shows the process activities that are enacted. 3, a practice perspective that suggests good practices to be used during the process. The RUP is a phased model that identifies 4 discrete phases in the software process. However, unlike the waterfall model where phases are equated with process activities, the phases in the RUP are more closely related to business rather than technical concerns. These are inception, elaboration, construction, and transition. I will not dive deep into details of each of the phases. Those are less relevant to this course and can be found in any literature on software engineering. The static view of the RUP focuses on the activities that take place during the development process. These are called workflows in the RUP description. There are 6 core process workflows identified in the process and 3 core supporting workflows. The RUP has been designed in conjunction with the UML, an object-oriented modeling language, so the workflow description is oriented around associated UML models. The advantage in presenting dynamic and static views is that phases of the development process are not associated with specific workflows. In principle, at least, all of the RUP workflows may be active at all stages of the process. Of course, most effort will probably be spent on workflows such as business modeling and requirements at the early phases of the process and in testing and deployment in the later phases. In our today's lecture, we have covered some of the traditional approaches to software engineering that are used nowadays. We gave definition of computer software, we talked about types of computer software, we gave description to software processes, common activities, introduced importance of models. We also provided a brief discussion on waterfall lifecycle, iterative life cycles, discussed their advantages and disadvantages, spiral model, and rational unified process were also introduced briefly for revisiting purposes. In our next class, we will continue with traditional approaches to software engineering. Thank you very much.